Non-quark model mesons include exotic mesons, which have quantum numbers not possible for mesons in the quark model, glueballs or gluonium, which have no valence quarks at all, tetraquarks, which have two valence quark-antiquark pairs, and hybrid mesons, which contain a valence quark-antiquark pair and one or more gluons. All of these can be classed as mesons, because they are hadrons and carry zero baryon number. If these glueballs must be flavor singlets, that is, have zero isospin, strangeness, charm, bottomness, and topness. One also specifies the isospin I of the meson. Typically, every quark model meson comes in two flavor nonet, an octet and a flavor singlet. A glueball shows up as an extra particle outside the nonet. In spite of such seemingly simple counting, the assignment of any given state as a glueball, tetraquark, or hybrid remains tentative even today. Even when there is agreement that one of several states is one of these non-quark model mesons, the degree of mixing and the precise assignment is fraught with uncertainties. There is also the considerable experimental labor of assigning quantum numbers to each state and cross-checking them in other experiments. As a result, all assignments outside the quark model are tentative. The remainder of this article outlines the situation as it stood at the end of 2004. Lattice predictions. Lattice QCD predictions for glueballs are now fairly stable, at least when virtual quarks are neglected. The two lowest states are 0++ with mass of 700316110000000001611 plus or minus 163 MeV, C2 and 2++ with mass of 7003223200000002232 plus or minus 310 MeV, C2. The 0- plus and exotic glueballs such as 0- are all expected to lie above 70020000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 with isospin I equals 0. The ground state hybrid mesons 0- plus, 1- plus, 1- and 2- all lie a little below 7002000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000made in the quenched approximation, which neglects virtual quarks loops. As a result, these computations miss mixing with meson states, the 0++ states. The data show 5 isoscalar resonances, F0, 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 and F0. Of these the F0 is usually identified with the sigma of chiral models. The decays and production of F0 give strong evidence that it is also a meson. Glueball candidate. The F0 and F0 cannot both be a quark model meson, because one is supernumerary. The production of the higher mass state in two-photon reactions such as 2-gamma-2-pi or 2-gamma-2k reactions is highly suppressed. The decays also give some evidence that one of these could be a glueball. Tetraquark candidate. The F0 has been identified by some authors as a tetraquark meson, along with the I equals 1 states A0 and kappa 0, two long-lived states. The scalar state D*+ or minus Sj and the vector meson D*+ or minus Sj, observed at Clio and Barbar, have also been tentatively identified as tetraquark states. However, for these, other explanations are possible. The 2++ states, two isoscalar states, are definitely identified, F2 and the F2. No other states have been consistently identified by all experiments. Hence it is difficult to say more about these states. The 1- plus exotics and other states. The two isovector exotics pi1 and pi1 seem to be well established experimentally. They are clearly not glueballs, but could be either a tetraquark or a hybrid. The evidence for such assignments is weak. The pi, ρ and the eta 2 are fairly well identified states, which have been tentatively identified as hybrids by some authors. If this identification is correct, then it is a remarkable agreement with lattice computations, which place several hybrids in this range of masses.